So we are looking at a first principles approach to finding the derivative. So just to remind you that the derivative is what we call the gradient function. And in preceding videos, we looked at the idea that we can look at the gradient of a function by looking at a change in y, which is what this top does, over a change in x plus h minus x would just give me the h on the bottom. So we have this expression here, which allows us to find the gradient of a secant. And the principle that we went through in the video, for those who watched it, was that if we allow h to get really, 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 really small, then we are getting closer and closer to what we would call the instantaneous gradient at a particular point. And based upon our previous lesson where we practiced limit theory, we've got this idea that although we can't directly evaluate the gradient at a particular point by setting h equal to 0, in other words, by making these two things the same, but then the bottom h would be 0, and we can't divide by 0. Although we can't do that, we can look at the behavior of the function as h approaches 0. Okay, so instead of setting x approaches 0, we're doing h approaches 0. So effectively what we are saying is as h gets really, 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 really tiny, what is the behavior of the gradient approaching? That's the idea, and we call that f dash of x. That's how we will say it. And it is the gradient function. So f dash of x is related to f of x by that definition. Okay, I'm not going to ask, are we good so far? Because if you don't get that, we'll put it like this. If you don't get that and you've watched the videos, please ask a question now. Great. Either you don't get it because you haven't watched the videos, in which case backfill with the videos, or you do get it and we can move on. So the example I've got here to illustrate this first principles approach is f of x equals x cubed plus x. And we're asked to find the gradient function and hence find the gradient at x equals 0. Oh, P.S., why do we keep calling it the gradient function? And that's because the result of this operation here is another function. And that function can be used to find the gradient at any point on a continuous graph. Okay, so that's why we do it, because we don't have a constant gradient, and therefore we need a function to describe the gradient through all of its places on the graph. Okay, so the video that you were supposed to watch for today went through the basics of the power rule. I'm happy to it's not a very difficult rule, but it's a bit magical in terms of how it works. But nevertheless, let's go for it. If we were asked to find the gradient function of f of x equals x cubed plus x, we go f dash of x, then we bring down the power and multiply it by the whole term. So if there was a 2 here, then that would be 3 times 2, which equals 6, but there isn't. So we just bring down the 3. 3 times 1 is 3, x, and then we subtract 1 from the power. So we've got 3x squared. Now, x here does have a power. It's an implicit power. What power is x, Josh? Yep. So we bring down the 1. In this case, I will write it in. And then 1 minus 1 is 0, and anything to the power of 0 is 1, okay? So effectively, we would have 1 times 1. So bottom line is that x will become a 1. So you can see we've gone down by 1 power for each of the terms of that expression there. Is that okay with everyone? That is the gradient function. Once we have the gradient function, we are able to work out the actual gradient at any point. So I can go at x equals 0, f dash of 0 is equal to 3 multiplied by 0 squared plus 1, which equals 1. i.e., at the x-intercept, the gradient is equal to 1. Sorry, not the x-intercept. At the y-intercept, the gradient is equal to 1. That's all it means. It's got a gradient of 1. 1 for 1 gradient. Rise over run, The rise is equal to the run at that point. Okay, any questions? Easy as, huh? It pretty much is. The power rule is easy. The difficulty is not necessarily using the power rule. The difficulty is often in interpreting the power rule, using it in different ways. However, you also need to understand how to do it from first principles. So that's what we're going to do here. So strap in. F of x is equal to x cubed plus x. Get that down first. I'm going to switch back to the other screen for a second. If you have a look at the first principles approach, you'll see we've got limit as h approaches 0. Remember how I said yesterday in class, make sure you've got that on every single line of your working out until the end. So we're going to do that, but we're not there yet. If you look at the components of this, we have an f of x plus h, and f of x, and an h on the bottom. So I have learned over time that many students find it easier to deal with each of those components first and then putting it all together in that fraction. So that's what we're going to do. You don't have to do it this way. You could go straight into the fraction work if you're feeling comfortable. So we've got f of x is equal to x cubed plus x, f of x plus h. Now, I want you to remember the transformation work we've done. This is one of the reasons why we do this transformation work, so that we can bring it all together for reasons like this. Remember that f of x plus h means replace the old input, x, with a new input, x plus h. Okay, it is a swap. It's a swap around. Okay, or an exchange. So wherever there's an x in f of x, we're replacing it with x plus h. So that becomes x plus h, all cubed. Instead of x cubed, it's x plus h cubed. And instead of x, it's x plus h. Technically, I don't need the brackets on the right-hand side there, but you'll see that go in a second. Okay, any questions on that? All right, another tool we need to use. How do we expand x plus h all cubed? It's not x cubed plus h cubed. Don't make me cry. What tool? You don't have to know what it is. What tool would we use to expand that? Slow way would be to do an expansion of an expansion, right? We could split it up to x plus h times x plus h times x plus h and expand it out. Do you have an idea? No, we're not using the power rule because we're trying to, well, number one, you can't use the power rule because the power rule only works when you've got x to the power of 3. This is an expression to the power of 3. So you can't use it directly anyway. You do learn techniques to do it, but that's not the point anyway. We're not finding the derivative. We're finding f of x plus h at this stage. So power rule is not that. I'm talking about an algebraic technique to expand x plus h all cubed. Do you reckon you know? Perfect. Thank you, Harry. Pascal's triangle is the expansion technique. Now, this is where you need to realize that mathematics is not siloed. You can't say, well, in the algebra unit, I did Pascal's triangle, and everywhere else, I don't even have to think about it. Okay? You will be a weak mathematician. The idea about the algebraic unit is to give you this set of tools so that you can apply it in other situations. It's useless by itself, but when you bring it into other areas of mathematics, that's when it starts to really do its thing. So for those who can't remember, we can build Pascal's triangle like so. And there are our starting coefficients, 1, 3, 3, 1. And so I'm going to go equals x cubed, that's 1, plus 3 x squared, bringing the powers of x down by 1. I'll even expand it so you can see it. No, I won't, because then you can't see Pascal's triangle. 3x squared h, 3xh squared, plus 1h cubed. So again, 1 is implied, 1, 3, 3, 1. Cubed, squared, 1, gone. gone, 1, 2, 3. Okay, so that's a standard Pascal's triangle, plus x plus h. Okay, do we have any like terms there? Not really. There's no like terms there, so we can't simplify that any further. So now we've got our f of x plus h, and we've got our f of x. Just going to get rid of that Pascal's triangle since we don't need it anymore. So therefore, f dash of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. You don't technically have to write that in, and it is on your information sheet. Now we're simply going to replace f of x plus h with that expression we worked out, and we're going to replace f of x with the expression that we were given. Now, I'm going to put my equal sign over here because it's quite long. Normally, you put your equal signs underneath each other. So that is equal to. Note that the equal sign is first. Then we write limit as h approaches 0. Okay, so I often see the equal sign on the other side of the limits. That's not right. It's like a sentence. It is equal to the limit as h approaches 0 of f of x plus h. Wish me luck as I write it down. X cubed. Is that too small? Everyone okay with that? X cubed plus 3x squared h plus 3xh squared plus h cubed. I'm literally just writing it down. That looks too small, but no one's complained. Minus x plus h. Keep those brackets in for a bit. If you don't put the brackets around... Oh, sorry. Don't write that down. Don't write that down. My bad. Plus h cubed plus x plus h. Okay, so that's f of x plus h minus f of x, x cubed plus x. So sorry. All over h. Give you a chance to write that down while I talk about it. Keep the brackets around the expression for f of x for at least one line. It is one of the most common mistakes that people don't put a subtraction around, so don't put brackets around f of x, and they often forget that a minus and a plus becomes a minus, and we'll see that in the next line. I'm not going to get rid of those brackets. I'm going to just assume that you can see what we're doing in this next step. Now have a look. The x cubed here will be eliminated with the x cubed here. So x cubed minus x cubed is gone. The x here will be eliminated. Even though it's a plus x here, we've got a minus outside the bracket, so it becomes a minus x. So the x's will also be eliminated. I'm going to zoom up, actually, because I'm so sorry. I didn't mean to make it that small. That's what I'm doing. Yeah? So what are we left with? Everything else cannot be eliminated. So we're left with the limit as h approaches 0 of 3x squared h plus 3xh squared plus h cubed plus h all over h. Okay, so we end up eliminating effectively the highest powers of each of the terms. So the x cubes get eliminated and the x gets eliminated. And so that's why we end up with something which is one power less, because the actual powers themselves, the original powers, get eliminated by this first principles approach. Okay, so you might remember from our work on limits yesterday that we can't set h equal to 0. We can't evaluate h at 0 until we eliminate the impossible. The impossible, of course, being a fraction over h. I'm going to have to zoom out again now. And I'll stay zoomed out so we can see it all connecting together. So we've got f dash of x is equal to, we need to get rid of that h. And I don't know if you can see it or not, but there is a common factor of h in the numerator. Every single term in that numerator has an h in it. So I can take h as a better put the limit as h approaches 0 in. I can take h as a common factor out, and that leaves me with 3x squared plus 3x h plus h squared plus 1 all over h. And I can then cancel out the h's. Now we're cooking with gas. This gives me the limit as h approaches 0, and because I no longer have a single fraction on the right-hand side of the limit, but I'm taking the limit of the whole expression, I need to put brackets around it. So that's the limit as h approaches 0 of 3x squared plus 3xh plus h squared plus 1. We now have eliminated the impossible, dividing by 0. So now we can set h equal to 0 and see what we've got. So we no longer have this anymore. We don't put that in. And we can see that this term has no h's in it. So that'll be 3x squared. This term has an h in it. So 3x times 0 is 0. H squared, 0 squared is just 0. So we don't need to worry about these terms anymore. They're gone. And 1 is not affected by h being set equal to 0. So we have 3x squared plus 1. And then you wipe your brow and say, that was a lot of hard work. Just to confirm, by the power rule, f dash of x equals 3x squared plus 1. By first principles, f dash of x equals 3x squared plus 1. It would be a real bummer if we didn't get the same value, the same expression out of it. So there's our gradient rule. And by first principles, now that I've got my gradient rule, I can now use it to work out when the gradient is equal to 0. The rest of the process would be exactly the same. You would set x equal to 0, and you would say the gradient at x equals 0 is 1. All right. Does anyone have any questions on that? Because you're about to practice it, so you have to ask questions now so that you get it as clear as possible. So again, the steps are, this is the way I would do it. F of x, write it down. F of x plus h, replace x with x plus h, and then do what you need to get a to get an expression. Put them into the fraction, simplify the numerator, and almost always, no, not almost always, you should always get a common factor of h at some point so that you can cancel out the impossible, and then you can set h equal to 0. Note that lim is here, 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 and here, all the way until we set h equal to 0. I'm going to put a red star next to the steps that I think everyone should do as a minimum. That one, that one, that one, and then that one. Okay, this one, because it shows that you can substitute in. This one, because you've simplified it. This one, because it shows the cancelling out of the impossible step. And then this one is like, okay, so I've set h equal to 0, there's my answer. That's a bare minimum. Many of you will want to do this setup first, and I would encourage you to do so, but I'm not saying it's required, but I would encourage you to do so to eliminate mistake making. Some of you might want to miss this step, but I think you're not setting yourself up for success if you miss this step, because there's too many minus issues that can happen here. This one can technically be missed because as long as you show the cancelling out bit, you can go from there to there without much of a drama, because cancelling that out basically leaves you with that bit inside anyway. So you can technically miss that out without showing clarity. if you miss out this step here, if you go from here to here, you will not get full marks in the test. And the reason why is pretty simple. It's too easy to pretend you know what you're doing and then just use the power rule to get me the final answer. Okay, so you need to show that you understand about the elimination of the impossible in order to work out the first principles approach. Okay, so which way would you prefer to do it? Power rule or first principles? First principles, right? Says only the insane. Of course you'd prefer to do the power rule. I certainly use the power rule all the time. First principles I would only do under certain circumstances. So I thought I might just spend a moment to explain why we might do it. First of all, oops, won't use red. It allows you to find the derivative of unfamiliar functions. Okay, so the power rule, I mean, there are lots of rules, right? So you do learn lots of rules anyway. But the only reason why you've got the power rule is because someone figured it out from first principles. But once you've got the rule, then you can use it. But I don't have to do much to make the power rule not work. You can't directly use the power rule on that. But if I expanded it and stuff, I could. We've got no chance of using the power rule for that. It's just not the same. Or this. So the power rule is only useful if you've got the sum or subtraction, like a bunch of terms, powers of x, effectively, or x to the powers of. That's the only reason why time you can use the power rule. Even if you've got like this, you don't know how to do this year. You won't learn how to do this year. Doesn't look that much different, but you can't just find the derivative of each bit there because that division in the middle, that fraction, makes it a different problem to what the power rule can solve. The power rule can literally only solve something like that. So it's versatile, but it's only for power functions. Functions where you've got x to the power of something. Sums and minuses and whatever else, but not multiplications and divisions. Not directly anyway. We do have some workarounds, which we're going to learn during this course, but more or less, there's not much you can do. So it allows you, first principles allows you to work out different rules for different functions, some of which you might not know. The other one is just a typical eye roll teacher comment, which is that it gives you an understanding of how it all works. I think I've mentioned this before. With no offence to grade 6 students, I could definitely go into a grade 6 classroom, tell them the power rule, illustrate it with a few examples, and get them to practice working out the power rule over and over and over again until they can always find the gradient function. I could do that in your grade 11s. So the point is that if I asked a grade 6, now explain what that means. Explain how we got that. That's when things become more challenging, right? So the power rule is simple, but if you don't understand that in the background, effectively what it's doing is it's finding the gradient at a point by considering the behavior of the gradient as we decrease the secant to a single point. That's pretty complex stuff that I wouldn't expect a grade 6 to be able to handle, whereas you guys can. Okay, so the first principles approach actually illustrates what we're doing there, and we can see that we're always eliminating, like x cubed and x, they always get eliminated, and we're left with, because of the way Pascal's triangle works, we're left with one less power. So we've got x squared here. we've got a 1 here. So we can see that in operation, that why the power rule works is because of effectively how Pascal's triangle works, which is pretty amazing little link. And the third reason is because, and this is the one that students want to know, I hope some of you appreciate the second dot point. This is the worstest reason at all to learn something, but nevertheless, the one that speaks to students a lot, because you can be tested on it. There will be a question in the test that will have a first principles question you need to do. The exams almost always, in fact, I can't think of an exam where it hasn't, like external exam, where it hasn't actually given you a first principles question to do. They're not normally that hard. Like, they're not even an X cube really, because they take a lot. Oh, sometimes they're a cube. They wouldn't go further than the cube though, because then it's just takes a long time to solve. But nevertheless, you are almost always asked. The good news is, although I want you to practice it, and I think it's important for you to get the mechanics of it because of the reasons I put on the board, if at the end of the day you don't get it, you're losing a few marks and that's about it. It's not a major part of the course. It's just an important learning structure, I suppose, for why differential calculus works the way it does. Okay, I'll stop the video there.